This week we look at the median and the taxicab metric. These are ideas that we'll use when we go on next week to look at linear regression. First of all, let me recall the notion of the mean. If you've got a collection of real numbers, the mean is simply obtained by adding them up and dividing by their number. Assuming here we've just got a finite number of real numbers. Now, this is a standard formula you've all seen from high school, and notice that if each of the numbers is regarded as occurring with equal probability 1 on n, then the mean is just the expected value. But the mean has an important optimization interpretation that's often not explained in basic introductory subjects in probability or statistics. The mean is the unique number that minimizes the sum of squares of the distances from that number to the given numbers xi. Now, it's important for us because this course is about linear programming, which is an optimization problem. So here we see that this classic concept of the mean is an optimization problem, but it's not a linear programming problem because here we're optimizing the sum of the squares. That's very non-linear. But there's another concept which is similar to the mean, and that's the median. And this is widely used in statistics. And part of the reason is we'll see that it's quite a robust statistic. And the mean is of a collection of real numbers is simply the number in the middle. So if we order the numbers in the natural way, if n happens to be odd, it is the middle number. So if the numbers are x1 up to xn, it's xn plus 1 on 2. If n is even, there's no middle number, but instead we could take the median to be any real number in the closed interval between the two numbers closest to the middle. Now the median has this useful property that it's not affected by small changes to the data. So just for an example, consider the numbers 1, 2, 3, 4, 5, 6, 7. So there are 7 numbers, that's odd. The one in the middle here, 4, is the median. Now let's change 7 and replace it by 21. So the numbers now, just like before, but the last one is much bigger. The one in the middle is still 4. The median hasn't changed at all. The mean, of course, will change. The mean changes a lot. So this shows that the median is more robust in the sense that it's less sensitive to experimental errors in the data. The downside of the median is that it's not uniquely defined when n is even. We'll see that this little subtlety will be important in this week and next week when we look at other issues. Now we've seen that the mean can be written as an optimization problem, and the median can also be written as an optimization problem. The median, which will denote x tilde, whereas previously we had the mean was x bar, the median x tilde is the special number x that minimizes the sum of the absolute values of the distances between x and the numbers xi. So the mean was minimize the sum of the squares. The median minimizes the sum of the absolute values. That is, if the numbers are x1 up to xn, and we look for the number x such that the sum of the absolute values of the differences is minimized. Now, this can be written as a linear programming problem in a rather clever way. The idea is to introduce new variables for each of these absolute values. So Zi is the absolute value of x minus xi. Now, as a function of x, Zi is obviously not linear because the absolute value function is not linear. Nevertheless, we can rearrange the problem into a linear programming problem. And the trick is to notice that the smallest Zi, that Zi is the smallest number for which x minus xi is less than or equal to Zi and xi minus x is less than or equal to Zi. That's just the definition from the definition of the absolute value function. So finding x to minimize the sum of the absolute values is the same as minimizing the function y, which is the sum of the z's, subject to all of these inequalities, which are the inequalities telling you that zi is the absolute value of x minus xi. So that's a very clever scheme. Now, you might think that that if you're given a bunch of numbers, to find the median, you just look for the one in the middle. That's a lot easier than writing it as a linear programming problem. And in many cases, you're right. You notice here in particular that the x variable will appear here half the time with positive sign, half the time with negative sign. And so when we rearrange these variables so that the xi are on the right, we're going to see that in half of the occasions the inequalities are bad, in the sense that we'll need to introduce artificial variables, so that not only are there a lot of inequalities, but there are a lot of bad inequalities, and switching to do the dual problem is not going to change anything because the number of bad inequalities is exactly half the number of inequalities. So the linear programming problem is not easy. Nevertheless, it does happen that for very large numbers, so when n is very big, the linear programming method can be useful. I mean, the thing is that if you've got a very large number of data points and they're not given to you in an ordered form, in order to find the median, you'd have to order the numbers. And that's not, that's quite a time-consuming process. We'll return to this practicality question later on. It will be useful next week as well. Now, so here I've just explained about the number of variables and the fact that in order to implement this program, you'd need to have n artificial variables, so you'd need to use Big M or two-phase. Now, one application of the median is the so-called facility location problem in using the taxicab metric. The taxicab metric, also commonly known as the Manhattan metric, gives a notion of distance which is not the usual one. And so here, the notion of distance between two given points, so here are two given points, and that taxicab distance between them is the distance along in the x direction plus the distance in the y direction. In other words, it's the sum of the differences in the sum of the absolute values of the differences in the coordinates. So in this example here, the taxicab distance between 1, 1 and 5, 6 is 9. And the facility placement problem is given endpoints in the plane to find a location which minimizes the sum of the taxicab distances from that point to the given points. So the idea is that the given points P1, P2, etc. might correspond to location of, for instance, shops in a chain of shops, and you're trying to find a point P to locate the head office so that the head office is located at a point which minimizes the sum of the distances to the particular shops measured in the taxi cab metric. And this problem has a particularly simple solution. You just take the median of the x coordinates of the points and the median of the y coordinates of the points, and they give you the coordinates of the solution point.